We consider our example here again of the region bounded by root x, 0, and x equals 4. Sketch this out here. Oops, let's sketch this out a little differently actually. Here we go. 1 and 1, 2, 3, there's 4. So we have our region bounded by y equals 0, bounded by x equals 4. That's our region. This time we're going to rotate around the line x equals 6. And again, just remember x equals 6 is this point here, but if we define it as a line, it's actually a y or a vertical line, all with the same x values. That can be a little counterintuitive for some people. But just remember x equals 6 is all these points. They all have in common that they have the same x coordinate with any possible y coordinate matching it. And we're going to spin around that axis. And what that's going to give us is a little plate shape like this with a hole in the middle, like so. So this will get spun around and we'll have a symmetric shape on the other side when we're done. And the three-dimensional view would look something like that shape there. Okay, our goal, of course, is to find the volume of it. And so how do we do this? We're going to decide on which way we're going to slice, because horizontal slices will give us circular type shapes. That's the way we're going to cut. So we're going to cut this way. That makes our slices delta y thick. And we ask ourselves then what the volume of a slice is. Well, if we slice that way, notice that that's going to continue on into the other side. And what does the slice look like? The slice is going to have an outer radius and an inner radius. There's a hole in the middle. And so we're going to have the volume being broken down into the area of a ring times the thickness. Let's add the thickness on here. And we've already seen a few examples of that. So the thickness is easy. It's a little thickness of delta y. The area of the ring is the area of an outer circle, so this whole region, minus the area of the inner circle. And those are just pi r squareds and pi r squareds and delta y for the thickness. Okay, our challenge then is to go back to our diagram and decide how are we going to get these radii. Now this is a little more intricate. Let's see how we can do this. Remember the relationship between coordinates and distances. This distance here, from here to here, is going to be 6, because we said x equals 6, well that's 6 units away from the axis. The radii we need are these distances, that's inner, and that's outer. The inner radius is nice and simple. It's always 6 minus 4. That's always 2. Okay. How about the outer radius? Well, there's a nice relationship here that if we talk about the point on the curve, well, that's what defines the boundary. That's why we stop here, is because we hit this curve. This distance from the axis out to the point is x. And so the distance remaining is the entire distance, 6, minus our x coordinate. So our outer radius is 6 minus the x part there. Let's see how that plays out. So we'll have pi, outer radius is 6 minus x, all squared. The inner radius, the distance from the center of rotation here out to that central core, is always 2 units, and delta y. That's actually most of our work now. The only challenge being to convert our x values here to y, so we only have one variable. But that's fairly easy to do because our curve, this x value, is on the curve y equals root x, or y squared equals x. So if we know what the x value is, we know what the y value is. And so we can replace this through y squared equals x and we get pi 6 minus y squared, still all squared, we don't change that, times 4 pi delta y. So, just a quick recap. Each slice, we're going to slice horizontally because that's how we're going to get circles. Vertical slices would be some crazy, crazy shapes. We don't want that. So horizontal slices. What does each horizontal slice look like? Because the region we're talking about is not butting up against the axis of rotation here, there's a gap, we're going to have a hole in the middle of each ring. And so we're going to have to find the volume of these rings rather than the volume of a cylinder. That's pretty straightforward. We just need an outer and inner radius, and we can use those with the circle formula for area, and we get the area of the ring. Then we focus in on our diagram and say, what are those radii on a particular slice? If I knew what my y value was, could I find the radius? Well, the inner radius doesn't depend on y, it's easy, it's always 2. The distance between the boundary, x equals 4, and the axis of rotation, x equals 6. And I don't do this mostly mathematically, honestly. I do it with the diagram and just say, hey, how far is it from 4 to 6? Hey, it's 2. Okay. That also helps when we're trying to find the outer radius. When we've got the outer radius, it's this distance from here to here. I can see it on the diagram. That's how big the circle is. It's going to be the distance from the center out to that outer range. What's that defined as? Well, it's going to be 6 minus that x coordinate. Now, with the volume of each slice in hand, we can create our integral that'll compute the total volume of this entire shape simply by adding up those slices, the volume of those slices, to get the total volume. Our total volume will be the integral of what we had on the last page, which was pi 6 minus y squared squared minus pi times 2 squared, which was 4, and all of that times dy. For the limits of integration, we go back a page and we look at the diagram and we notice that we're integrating from y equals 0 to y equals 2 would be the upper limit. It's important to note that we're just reading these coordinates off of the diagram itself. So where's the first slice that we would take that looks like this? It'll start at y equals 0. Where's the last slice? At y equals 2. It is that simple to read off the limits. So we have y equals 0 up to y equals 2. Now, just a little bit of simplification before we start the actual integration process. Everything has a pi, we can bring that out front. We have 36 minus 12y squared plus y to the 4th minus 4. That's the expansion of our 6 minus y squared all squared. And so pi 0 to 2, 36 minus 4 is 32. And we are good to go. Everything is integrable. This should be in y to the 4th. And 32y minus 12y cubed over 3 plus y to the 5 over 5. And that evaluated at 2 and at 0. If we do that, we get pi times 32 times 2 minus 12 times 8 over 3 plus 2 to the 5 over 5. All of that minus plugging in 0 gives us 0, 0, 0. Fortunately, that's nice and simple. And we can go to our calculator for this and find the answer. We get the value of approximately 120.6 cubic units. So that shape with a hole down the middle, rounded off and spun around, will have a total volume of 120.6 cubic units.